The topic is electrophilic aromatic substitution. Benzene has 6 pi electrons which are delocalized in 6 p orbitals that overlap above and below the plane of benzene. These loosely held pi electrons make the benzene ring so much rich of electrons, so it will react only with the electrophiles. Because of these pi electrons, benzene satisfies Huckel's rule and it is very much stable. So generally it will undergo the reactions which will cooperate to have an intact of these pi electrons in the benzene ring. Benzene doesn't undergo any addition reactions like other alkenes, but addition would yield a product that is not aromatic, whereas substitution of hydrogen on the other hand keeps the aromatic ring intact. As a result, the characteristic reaction of benzene is electrophilic aromatic substitution, where the hydrogen atom present in the benzene is replaced by any electrophile and forming the substituted benzene product. Here, the benzene ring is intact and it will not destroy the Huckel's rule, making it as a stable product. Generally, there are 5 examples for this electrophilic aromatic substitution, and the basic mechanism involving for all 5 reactions are same. The reactions differ only in the identification of electrophile formation. Now we will discuss all the 5 electrophilic aromatic substitution reactions one by one. The first one is halogenation. In halogenation reaction, the hydrogen which is present in benzene will be replaced by any halogens. General halogens are chlorine and bromine to form aryl halides. Next one is nitration. So here the hydrogen atom will be replaced by a nitro group which is formed by using a catalyst like HNO3 and H2SO4 to form nitrobenzene. So the electrophile used here is a nitro group. Third reaction is sulfonation. Here the replacement of hydrogen atom present in benzene will be done by sulfonic acid to form benzene sulfonic acid, and the catalyst used is sulfur trioxide and sulfuric acid to form sulfonic acid as an electrophile. The fourth reaction is Friedel-Crafts alkylation. Here also the hydrogen which is present in benzene ring will be replaced by the alkyl group and it will form alkyl benzene, also called as arene moieties. Here the reaction will proceed by reacting alkyl halide with Lewis acids like AlCl3 to produce R+, which is an electrophile, to form alkyl benzene. The next reaction is Friedel-Crafts acylation. Here the hydrogen atom present in benzene will be replaced by any acyl group and it will form a ketone. Reaction proceeds by reacting the any aryl halide with AlCl3 to produce this acyl group as an electrophile, that is RCO+. To understand these reactions, we will look into the general mechanism of electrophilic aromatic substitution. No matter what electrophile is used, all the electrophilic aromatic substitution reactions occur via a 3-step mechanism. First step is formation of electrophile. Any reagent can be expressed as ENU, which will react with catalyst to form electrophile, and a byproduct, that is NU catalyst, which will behave as a base and utilized in step 3. The step 2 is addition of electrophile to form a stabilized carbocation. Here, the addition of electrophile forms a new Ce bond using the 2 pi electrons of benzene ring and generating a carbocation. The carbon-cation intermediate is not aromatic, but it is resonance stabilized by 3 resonance structures. The step occurs very slowly and it is called as rate determining step, followed by the third step, that is deprotonation of benzene ring to form the substituted product. The base removes the proton from the carbon-bearing electrophile, thus reforming the aromatic ring. This step occurs very fastly and restoration of aromaticity ring of benzene is done. For better understanding, we will see the energy diagram of electrophilic aromatic substitution. Here, the benzene ring is having lower energy, and when electrophile attacks on it, it reaches the highest energy transition state. Because of that, it loses its aromaticity, and this is considered as rate determining step, followed by the third step where the base removes the proton from the carbon bearing electrophile, thus reforming the aromatic ring. This step occurs fastly and is not considered as rate determining step, and here the aromaticity of benzene ring is restored, finally forming at the low energy state. Let us discuss one of the electrophilic aromatic substitution, halogenation. In halogenation, the benzene reacts either with chlorine or bromine in presence of a Lewis acid, that is FeCl3 or FeBr3, to give aryl halides chlorobenzene and bromobenzene. Analogous reactions with iodine and fluorine are not systematically useful because I2 is too unreactive and F2 reacts too violently. So fluorine and iodine attack on benzene can't be happen that much easily when compared to chlorine and bromine. Mechanism of bromination. Here, generation of electrophile occurs by reacting bromine molecule with FeBr3, which is a Lewis acid, to produce a molecule which serves as a rich source of Br+. Step 2 involves addition of this electrophile Br+ onto the benzene ring to form a carbocation. This carbocation can be written in three resonance structures forms along with the formation of FeBr3, which is considered as a base and used in step 3. Step 3 involves the loss of proton to form reformation of aromatic ring. Here the FeBr4 minus, which is formed in step 2, act as a base and it abstracts the proton from the benzene ring and results in the formation of the substituted benzene ring, that is bromobenzene, with reforming the